Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. Ramgopal, welcome you all to the today's session on Taylor's series part 2. In the last session, we have obtained the Taylor's series expansion of the given function of complex variable about a point z equal to a or in powers of z minus a. So for that, we have used a shortcut method, or the important point to be noted to obtain the Taylor series is simply, if you want to expand about a point z equal to a, then z minus a equal to w. From this, find the value of z as a plus w and replace this in f of z. Then use the standard expansions like 1 by 1 plus z, 1 by 1 plus z whole square, 1 by 1 minus z, 1 by 1 minus z whole square, or else sin z, cos z, e power z. So using such standard expansions, we can find the Taylor series expansion of the given. And also there is another procedure, just using the actual statement of the Taylor's theorem. So by Taylor's theorem, f of z equal to f of a plus z minus a by 1 factorial f dash a plus and so on. So here the power of this z minus a increases, and here if we have n z minus a power n, then nth derivative must be here f power n of a by n factorial. So that is the nth term of this series. It's an infinite series. So either you can use the actual Taylor series expansion, that means by finding the successive derivatives we can expand the given function as a Taylor series, or else if it is required to find about a point or in powers of z minus a, then you can use this procedure also. In the last session, we have obtained the Taylor series using this first procedure. Now today I am going to explain finding the Taylor series expansion using the statement of the Taylor's theorem itself. So coming to the first problem, f of z is 1 by 1 plus z square about z equal to I. So f of z is 1 by 1 plus z whole square. Now by the Taylor's theorem, this f of z can be obtained as a Taylor series expansion as f of a plus z minus a by 1 factorial f dash a plus z minus a whole square by 2 factorial f double dash a plus so on, plus z minus a power n by n factorial f power n of a plus so on. It's an infinite series. So let us use this statement of this theorem to obtain the Taylor series expansion. Here given the value of a is I. So we have f of z is 1 by 1 plus z whole square. Then what will be f of I or f of a, which is f of I, is 1 by 1 plus I whole square. And then let us find the successive derivatives. F dash z is the derivative of d by dz of 1 by 1 plus z whole square. So d by dz of 1 plus z whole power minus 2. So using the formula of derivative of z power n, this is equal to minus 2 into 1 plus z power minus 3. So minus 2 by 1 plus z whole cube. Now similarly, we can calculate the second derivative also. Again we need to differentiate this one. So minus 2 into derivative of d by dz of 1 plus z power minus 3. So this minus 3 comes here, plus 6 and by 1 plus z power minus 4. So which is plus 4. In numerator we will have minus 4, so this is plus 4. Similarly, we can find the remaining and the general nth term. So f power n of z, the nth derivative of the function f power n z is minus 1 power n n plus 1 factorial by 1 plus z power n plus 2. Now, by substituting n equal to 1, you can get this one. N equal to 1 with minus sign, 2 factorial, which is 2 by 3 whole power 3. Now put n equal to 2. This becomes positive sign, and 3 factorial is 6. 1 plus z power 2 plus 2 is 4. So let us find all these derivatives at I. Now f dash at I is equal to, so where is this z, in place of z we have to replace it by I, minus 2 by 1 plus I whole cube, f double dash I 6 by 1 plus I whole power 4, and so on. F power n of I is minus 1 power n plus 1 factorial by 1 plus I power n plus 1, n plus 2. So substituting this in the given function, so what is the formula? F of z is z minus a, f of a plus z minus a by 1 factorial f dash a plus z minus a whole square by 2 factorial f double dash a plus so on, and the nth term is z minus a power n by n factorial, nth derivative at a plus so on. Let us substitute all the values. F of a is 1 by 1 plus I whole square plus z minus a by 1 f dash at I. So with minus 2 by 1 plus I whole cube plus z minus a whole square by 2 into f double dash 6 by 1 plus I whole power 4 plus so on, plus z minus a power n by n factorial into minus 1 power n into n plus 1 factorial by z minus a power n plus 2 plus so on. So again simplifying this, we get 1 by 1 plus I whole square minus 2 into z minus a by 1 plus I whole cube, here 3 times, so plus 3 into z minus a whole square by 1 plus I whole power 4 plus so on, and here n factorial gets cancelled here, so this is minus 1 power n z minus a power n into n plus 1 by z minus a power n plus 2 plus so on. So this is the final Taylor series expansion of the given function. What is the given function? 1 by 1 plus z square. So 1 by 1 plus z square can be expanded like this. Similarly, there is another problem. This problem we can use the standard procedure of expanding using the known expansions. So here f of z equal to z square minus 1 by z plus 2 into z plus 3. If you expand this using partial fractions, we get 1 plus 3 by z plus 2 minus 8 by z plus 3. So this is f of z. Now to expand this we can write as 2, you can take 2 common in the denominator, so that we get 1 plus z by 2 minus 8 by 3 common 1 plus z by 3. So this is 1 plus 3 by 2 into 1 plus z by 2 power minus 1 minus 8 by 3 into 1 plus z by 3 power minus 1. So this is equal to 1 plus 3 by 2 into 1 minus z by 2 plus z square by 4 minus z cube by 8 plus so on. This is for first expansion. 1 plus z power minus 1 expansion. Replace z by 2. Similarly, minus 8 by 3 into 1 plus z by 3. So 1 minus z by 3 minus plus z square by 9 minus z cube by 27 plus so on. So this is the Taylor series expansion using the known expansions. Similarly, let us find the Taylor series expansion of sin z about z equal to pi by 4. So here given function f of z is sin z and the value a is pi by 4. Now let us use the Taylor's theorem statement. By Taylor's theorem, f of z equal to f of a plus z minus a by 1 factorial f dash a plus z minus a whole square by 2 factorial f double dash a plus so on plus z minus a power n by n factorial f power n of a plus so on. It's an infinite series expansion. So we have f of z is sin z. So f dash z will be cos z. F double dash z minus sin z. F triple dash z is minus cos z. Fourth derivative is plus sin z and so on. And we need to find all these at a. What is a here? Pi by 4. So f dash at pi by 4, f double dash at pi by 4, triple dash at pi by 4 and so on. So f of pi by 4, that means sin pi by 4. Sin pi by 4 is 1 by root 2. Similarly, cos pi by 4, here cos z, so f double dash pi by 4 and minus 1 by root 2 plus 1 by root 2. This is minus again, this is plus again and so on. So substituting these in the expansion, f of a plus z minus a by 1 factorial f dash a plus z minus a whole square by 2 factorial f double dash a and so on. Sin z equal to f of a is 1 by root 2 plus z minus pi by 4 into 1 by root 2. The second one is plus, third one is second order derivative is minus. So minus z minus pi by 4 whole square by 2 into 1 by root 2 plus z minus pi by 4 whole cube. The next one again minus, so here it will be minus by 3 factorial 6 root 2 plus so on. So like this, using the Taylor series statement or the original expansion, we can expand the given function. So today I have discussed some problems of finding the Taylor series, using the actual theorem itself. So by finding the successive derivatives, that means if f of z is given, find f dash z, f double dash z, triple dash z and so on, and find all these values at z equal to a and substitute in the actual Taylor series expansion. So this is for today's session and we will meet in the next session. Thank you.